The Laplace domain expression for y of s may have complex roots in the denominator polynomial. If this denominator polynomial is quadratic with the coefficient b squared less than 4ac, then the roots of this denominator polynomial will be a complex conjugate pair. For example, for 1 over s squared plus s plus 2.5, the values of b1 and b2 are minus 1/2 plus and minus 3/2 j. If we were to use the Heaviside method to find the unknown coefficients alpha in the partial fraction expansion here, we would get complex numbers for alpha 1 and alpha 2. Instead, let's put y of s in the form of one of the entries in table 3.1. For example, we could use number 17, which is omega over s plus b squared plus omega squared. We set this equal to our expression for y of s. The s squared plus s terms in the denominator will have to be obtained from the s plus b squared. Since the coefficient of s here is 1, b must be equal to 1/2. Now this denominator s plus b squared plus omega squared is s plus 1/2 squared plus omega squared. If we square the first term, we get s squared plus s, which matches the first two terms on the right-hand side here, plus 1/4 plus omega squared. The 1/4 plus omega squared must be equal to 2.5. So omega squared must be equal to 2.25, which means that omega is 1.5. Now we can find the coefficient c that multiplies this entire term. Omega c must be equal to 1, so c must be 2/3. Therefore, y of s is 2/3 1.5 over s plus 1/2 squared plus 1.5 squared. This can be inverted using entry 17 in table 3.1. This method of resolving the complex roots in the denominator is called completing the square. Not surprisingly, we find that when we have complex roots of the denominator polynomial in the Laplace domain, that corresponds to oscillations in the time domain. In this case, the oscillations decay because the sine function is multiplied by an exponential decay. Next, we'll review some key properties of the Laplace transform. The transform and the reverse transform operations are both linear operations, meaning they obey the principle of superposition. You may find it valuable to use a property of the Laplace transform called the final value theorem. In the time domain, if y of t has a limit as t approaches infinity, that is equal to the limit of s y of s in the Laplace domain as s approaches 0. The final value theorem is only meaningful if the time domain function has a limit as t approaches infinity. A corollary to that is the initial value theorem, which says that if y has a limit as t approaches 0, then that limit is equal to the limit of sy of s as s approaches infinity. This can easily be used to check the solution when finding inverse Laplace transforms. If these two limits don't match, then you likely committed an error when inverting a Laplace transform. So we'll make use of these a lot to check answers. The real translation theorem is what we call the Laplace transform of a time delay. We've already reviewed this. The real translation theorem is represented by entry 26 in table 3.1. The convolution property involves the product of two functions in the Laplace domain. The product of two functions in the Laplace domain gives rise to a convolution integral in the time domain. Earlier we looked at the Laplace transform of an exponential decay, but we didn't look at the Laplace transform of an exponential growth. When capital F of s has positive real denominator roots, that is, the b are less than 0, then f of t will grow exponentially in the time domain. When f of s has complex denominator roots, that is, b squared are less than 0, then f of t will oscillate. Remember that complex roots of the denominator polynomial will always appear as complex conjugate pairs of roots. When f of s has an exponential in s, then f of t has a time lag or a time delay. That's the same thing as the real translation theorem, where here f of s has an exponential in s, which results in a time delay in the time domain. In the next video, we'll formulate an ODE model for a process, and we'll show how that model can be analyzed and solved using Laplace transforms.